All right, this is going to be the video on really what you missed in class or what should have been covered in class, but unfortunately, uh, those people came, right? And unfortunately, it's going to take place over a period of 3 days. Wow, it's it's great. It's perfect. It's great. Just great. Just goddamn great. But I still expect you to keep up with my other physics class. I'm not slowing down. I still expect you to keep up with it. So this entire new unit that we're going to go into is energy. That's this new unit. We're gonna finish this unit of energy before midwinter break. Your test is on the Thursday before midwinter break. So that's never gonna slow down. That's not gonna change. You must know about energy. And the first part of energy, we have to talk about work. We have to talk about work done on an object. And so, what does that mean exactly, right? What does that mean exactly? Well, in physics, work done is defined as a force applied over a certain distance. And on your reference table, if you look at the back page, if you look at the final page of your reference table, you'll see that work is equal to force times distance. Force times distance. And there's a I stress that d is distance because d cannot be displacement. For work at least. Work is a scalar quantity. It has no direction. Sure, force is a vector, uh, but if you in college we call this a dot product, and that's usually how I explain how I envision it in my head, and that's why it's a dot product, so it's a scalar quantity. But I'm not sure you guys understand what that means. So just know that work is a scalar quantity, and is a uh, work is a scalar quantity, and it's force times distance. Right? The d will always mean distance. Right? The d will always mean distance. And so I will attach a worksheet for you along on the Google Classroom page, and I expect you guys to fill this out. These are your notes, right? And so in physics, work is what? I give you blank space to write. Well, what I want you to write in that blank space, this entire thing. Well, minus the formula part because it's on your reference table. So I do want you guys to copy this down. And also know that your work is measured in joules. Work is measured in joules, right? And while there isn't a place for you to write it on the paper, I do expect you to know that work is measured in joules, right? So once again, work is defined as a force applied over a distance. This is your formula on your reference table. W is equal to Fd, and work is going to be your scalar quantity. Now, now we go into, well, if we do not apply a force on an object, meaning our force is 0, right? If our force is 0, well, the sensitivity is off on this. Oh, I know why. I know why. Give me a second. Let's see, where is it? All right, good. Give me a second. Give me a second. All right. Now, work. Sensitivity is perfect now. Work is force times distance. All right. And so, well, if we don't apply a force, that our force is 0, well then my work done is 0. And that's the answer to number 3. Well, if you have no force, 0 times d is 0. And so you don't have any work done on the object. And now this is number 3. And for number 4, if we apply a force on the object, so let's say our force is not equal to 0, and it doesn't move anywhere, but okay, not and it doesn't move anywhere. It doesn't move anywhere. So the distance you travel is 0. Well, what's my work now? What's my work done on the object? My work done on the object is now 0 because d is 0 and 0 times anything is going to be 0. And this is joules. And so even if you apply a force on something, let's say this bodybuilder, right? If she doesn't move it anywhere, if she doesn't move the barbell anywhere, then you're not going to move anywhere. But she does. She applies a force, she moves it a distance up, so she's doing work on this object, she's doing work on the barbell, right? She's pulling the object, applying a force, and that barbell is moving a distance. And so that must mean you are doing work. You are doing work on this object. All right. Now let's go to part 2. Part 2. And so this is the picture I gave you. Now, if Now, part 2, reading force distance graphs. And this is pretty simple. You're not really going to be asked much about this. You just need to know about it. So what is the formula for work on your reference table? I told you, work is F times D, force times distance. And number 2, well, what is the formula? Well, there's a typo here, first off. It's a typo. All right, let's save that. What is the formula for the area of a graph? And you'll know that the area of a graph, let's actually erase all this first. Let's erase all this. Okay. We know that force is the undo. Formula for work is W is equal to FD. Formula for the area of a graph, the area of anything is either your base times height, or if it's triangle, it's 1/2 base times height. Right, that's your area. Well, what's your base? What's your base on this right here? What's your base on this graph right here? Your base is your distance. Well, what's your height? Your height is your y-axis. And so your height is going to be your force. Right? Your height is going to be your force. And so your area, and since it's a triangle, your area is distance times force. That's basically F times D. Well, if area is F times D and we know work is F times D, guess what? Our work is our area on a graph. All right? So we can calculate work on an FD graph by just calculating the area, and that's that. Right? That's that. Wait, what? No, don't save. And then to reiterate what work is, if I apply a force on the desk, like a desk, for example, I was actually going to demonstrate this in class. If I apply a force on a desk and it doesn't move, do I do work on that desk? No, I'm not doing any work on the desk. It's not moving anywhere. It's not moving a distance, so I'm doing no work on the desk. But let's say I push a student, right? Let's say I uh, push Andy Kaba around, right? And he moves and he falls. If I'm pushing him, which means I'm applying a force, and he's falling, so he's moving a distance. So I did do work on Andy Kaba. All right, and so that's how I want you to think about it in the future. And work is a scalar quantity. I'm sorry, Andy. Anyway, all right. So part 3, number 1. And so now we want to start figure out how to solve problems involving work. Right, so let's look at number one. A horizontal force of 30 newtons eastward causes a 20 kilogram box to have a displacement of 10 meters eastward. And the total work done by the box by the 30 newton force is what? So A is the first step is figuring out what your knowns are, right? And so we know my first known, we know my force, my horizontal force is 30 newtons east. We know our mass is 20 kg, and we know our displacement, which it should be distance, by the way. All right, be careful that even though it says displacement, you have to take the distance. All right, and my distance is 10 meters. Those are my knowns. And so what am I solving for here? Right, what am I solving for? Well, I'm solving for work. And now we're going to use a formula. Well, we know work is force times distance. Well, plug in the numbers, 30, 10, and you get 300 joules. All right, and that's how we measure work. And so now we just figured out how to solve for work. So number two. How much work is done by the force lifting a 0.2 kilogram hamburger 0.5 meters vertically upward at a constant velocity from a table? Just to give you guys a reference on how much a kilogram is. A kilogram is a water bottle. A filled water bottle. So that's how much 1 kilogram is. That is one massive hamburger. Right? That's one massive hamburger. It's a massive American hamburger. All right. So, what are our knowns? What are our knowns in this problem? Well, we know my mass is 0.2 kg, and we know my distance that I travel is 0.5 meters, and I know it's traveling at a constant velocity. Alright, so it's constant velocity. You don't really have to write this down for your notes. I'm just writing it down so you guys make sure to remember this. And so what am I solving for here? Well, I want to solve for my work done. Alright, so C. If, well, here before we move on, we know that work is force times distance. Guess what though? What the hell? Where's our force? Right? Where's our force? We don't have a force here. Well, let's figure out how do we calculate force, right? How do we figure out what our force is? And so if you're lifting something, what are two forces acting on the object? Well, the first force is Fg. The other force is, well, if you're lifting something up, you're applying a force to it, right? Well, we're lifting something up. Sure, there's a normal force somewhere else, but that's not on the object itself. All right. So, and it's not resting on a surface either, so there's no normal force from the surface to push the object up. You're already off the surface, right? This hamburger is already on its way to your mouth. All right, it's already on your way to your mouth. All right, it's not on the surface anymore. There's a normal force applied back onto your hand, and so if you really want to get deep into it, if you apply a force on the hamburger, there's going to be a normal force applied back onto your hand. But we only care about the hamburger here. Now, these are the two forces, Fg and Fa. These are the two forces on the hamburger. Now, D. D says if the object is traveling at a constant velocity, what's the acceleration of your object? Your acceleration is 0. It's constant. We know that the definition of acceleration is changing velocity. Well, if your velocity is constant, your acceleration is 0. Well, let's look at it this way. Well, if my A is 0, then my F net must be 0 as well, because F net is ma. And then if F net is MA, then A must be 0 and F net must be 0. All right. So let's actually move this over. Give myself some room. Well, if F net is equal to MA, and the F net, the literal definition of F net is sum of all my forces. Sum of all my forces. Okay, and I can relate this to, well, F net is just FA and FG added together, right? FA and FG is added together. And if you're wondering why I put a negative sign here, it doesn't really matter, all right? I'm just putting a negative sign here because FG is negative, right? It's going downwards. I'm just putting negative there. But it is basically the sum of all your forces. And if you solve for this, right? If you solve for this, you add FG on both sides, right? You add FG on both sides, and then you can get FA is equal to FG. Well, now we just figured out what our force is. We want our applied force. We want to know what is the force that we're lifting this hamburger up to our mouth is. Right, we want to know what FA is. Well, we know FA is equal to FG. And we know FG is equal to mg, and mg can be ma as well. It's ma mg. It doesn't really matter, to be honest. So your mass is 0.2, and this is f, by the way. This is f, and g is m is 0.2 and g is 9.8. Just ignore that. Amazon package, this is 9.8. Just believe me there. 9.8. So you're going to get 0.2 times 9.8 is going to get 2. Right? It's going to get somewhere around 2. It's going to get somewhere around 2 newtons. Right? So that's your applied force, right? If Fg is equal to 2 newtons and Fa is equal to Fg, Fa is also 2 newtons. Now we can solve for the formula. Now we can solve for a problem. All right. So let me just rewrite my nodes. I travel a distance of 0.5 meters, and my force is my applied force, which is equal to my gravitational force, is equal to 0.2 times 9.8. Is going to be somewhere around 2 newtons, somewhere around 2 newtons. So now we want to solve for work. F 2.5, and I get 1 joule. So it just takes me 1 joule. Now that's how you answer that question. Remember, if I'm lifting something, the force that's being applied is equal to my force due to gravity. Because my net force is 0. Remember that. It's important. It's imperative that you remember that. Part 4, number 1. Now, a student applies a 30 Newton force, so let's figure out where our knowns are. 30 newtons is my force, constant speed, so my velocity is 5 meters per second. Was the work done? And so my time is 10 seconds. And so this is A. So B was a simple formula for D. Again, here we don't know what our force is. Actually, we do know our force. Here we don't know what our distance is, right? What the hell is our distance? What the hell is our distance? Turns out we have a formula for distance that involves it, right? We know that on your reference table, V bar is D over T. V bar is D over T. Now, V bar is D over T. And why can I use V bar? Why can I use average velocity and not VF or VI? Because it says constant speed. If my speed is always going to stay the same, let's say like 1 second, my speed is 5, and another second is another 5. Well, the average number of these two velocities, 5 plus 5 divided by 2, is still 5. So if you have a constant speed, your average speed is just that number. All right, it's just that number. So substitute into your work formula. If V is equal to D over T, then that must mean D is equal to V bar times T. All right, so we're just going to substitute it. And so this is C. We're going to substitute it into our work formula. All right, so if D is equal to V bar times T, well then work is equal to force times V bar T. And now we want to solve for the formula. And we want to solve for this problem. And now we get to D. 1D, not like distance D. So work is equal to F V bar T. F is 30. V bar is 5. T is 10. 50 times 30, 1500 joules. 1500 joules. Yeah, good, great, perfect. Done with this. Done with this. This is the end of the worksheet. Now, what's left to do is that you guys complete the homework assignment that I will also attach. Actually, not attach, I will put it in the homework assignment category, but I do expect you to do it. You don't have to print it out. You don't have to. Actually, I'll give a copy to you in class. I'll give a copy to you in class. But it will also be on Google Classrooms. So there.